Hello, in this lab experiment we observed the magnetic field of a bar magnet using a magnetometer app on our phones. So for our fundamental principles, we first had to observe the distance dependence of a bar magnet, so as you get farther away, the magnetic field will lessen. And so this equation, just Bmag is equal to the constant k times the distance to the power of n, which is the distance dependence constant. And we also have an equation for the vector magnetic field of a bar magnet, which will be later on used in our computational model. And the purpose of this lab is to observe the distance dependence and magnetic field of a bar magnet in an experimental and computational setup. And so for a quick overview of our experiment, as you can see over to the left, we start out by finding where the magnetometer is on our phone, and then sliding that along a meter stick to actually observe what the magnetic field is at certain points. And then our next part of the experiment was using 2-meter sticks to calculate what the vector magnetic field is at a 45-degree angle from certain points. And quick disclaimer, my phone does not sit flat on the ground, and I had to use tape instead of actual meter sticks, so if any of my actual measurements are off, that's exactly why. So for our experimental data, we can see all the data is off to the left, but the most important thing we want to look at is our graph, which according to the equation that's shown on the graph, just gives us our constant k and our constant n for the most part. And for our off-axis magnetic field data, we can pretty much see this data will give us our x component of the vector magnetic field, our y component that we had to correct, and our z component that we also had to correct. And so for our observations, I observed that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. And as the magnetometer moves closer to the magnet, the x component of the magnetic field does increase. And so here are our calculations for our distance dependent constant. We got that to be negative 2.5, which is the slope of the previous graph. For our constant k, we got the natural log of k to be negative 15.5. Of course, we raise e to that power, and we get k to be equal to 1.8 times 10 to the negative 7. And we got mu with rearranging a couple equations we were given to be 3.689 am squared. And here is our computational model. As we can see, the things that we had to edit, we visualized a magnet just using the actual measurements of the dimensions of the magnet that we had to buy. And we got mu from our previous slide that we calculated. And then we also created a function to calculate the magnetic field using any of the measurements that we input. And for this bit of code, pretty much we set an arrow scale and a distance that we want to observe at, and then we find the observation locations based on that distance and visualize arrows going in on-axis magnetic fields, and then, of course, perpendicular magnetic fields. And for this bit of code, we do pretty much the same thing, but for our 45-degree angle. So we had to put in dperp from our experimental measurements, and then we visualize a arrow and yeah, for our 45-degree measurement. And so these are the results that we got. We can see the orange arrows are on-axis magnetic fields, while our cyan arrows are our perpendicular magnetic fields, and then the low magenta arrow is our 45-degree angle magnetic field. And we can see all of the values of magnetic fields are given at the bottom. And so for our what if questions, so we oriented the setup to compensate for magnetic north. So what would happen if we hadn't done that? So the results would have been more heavily influenced by the Earth's magnetic field, making it difficult to tell what readings were from the bar magnet or what's from the Earth. And so the results would have just been inaccurate. And so what if we had two identical magnets that we stuck together? So the magnitude of the magnetic field would be larger. So we would be achieving, R20, R70, etc. at smaller distances. And that's it for my experiment, and thank you for listening.